So now we will see properties of beta function. Okay, and the beta function is defined as, this is the standard definition of beta function, that is beta m comma n is equal to integral 0 to 1 x raised to m minus 1 minus x raised to n minus 1 dx, where n and m are greater than 0. Okay, so we will prove property 1. And property number 1 is, we have to prove that beta m comma n is equal to beta n comma m. We have to prove this property. They can ask you in exam that you prove that beta m comma n is equal to beta n comma m. Then you have to prove it. Okay. So for proving this property number 1, we will take, let x equal to 1 minus y in equation number 1. This is our standard equation. So we will use this equation for proving the properties of beta function. Okay. So for that we will take x equal to 1 minus y. So from this we will get y equal to 1 minus x. And if we differentiate it, then we get, differentiating both sides, we get dx equal to minus dy. And also we have to change the limit. This is the limit of x. So whenever x is 0, y is 1 minus 0. So whenever x is 0, y is 1. And whenever x is 1, y is 1 minus 1, 0. Okay. So limits will be also change. So if we substitute this value in this equation, then we get beta m comma n is equal to 1 to 0. We have to write the limits of y because we are changing equation to y. Because we have to prove that beta m comma n is equal to beta n comma m. So we will change x terms to y terms. Okay. So integral 1 to 0. Then in place of x we have to write 1 minus y raised to m minus 1. And 1 minus x is equal to y. So y raised to n minus 1 and dx is minus dy. We will write this minus outside. Okay. Now there is one property of limit that whenever you change the limit, that is one property you have to remember, that whenever you change the limit, if a to b f of x dx is there, and if you change the sign, that is if it is positive, and if you want to make this integral negative, then you have to change the limits. Okay, so limits will change, b to a f of x dx. Okay, so this is the property. So here also we want, in order to get this equation, we have to take out this negative sign, and so for that we will interchange the limit and remove the negative sign from this equation. Okay, so if we remove this negative sign, then limits will change, that is 0 to 1 y m minus 1, 1 minus y raised to m minus 1 and y raised to n minus 1 dy. So from this we can prove that this beta m comma n is equal to beta n comma m, because we have converted this x terms into y terms. So they both are same. So from this we can prove that beta m comma n is equivalent to beta n comma m. Okay. So hence proved. Okay. So this is the property 1 of the beta function. So now property number 2. Here we have to prove that beta m comma n is equal to 2 integral 0 to pi by 2 sine raised to 2m minus 1 theta cos 2n minus 1 theta d theta. So we have to prove this property. So for proving this property, we will consider this equation 1, which we have considered in the property number 1. Okay, so we will write this equation here. Beta m comma n is equal to 0 to 1 x raised to m minus 1, 1 minus x raised to n minus 1 dx. Okay, we will use this standard definition of beta function. Okay, now to prove this property, we will substitute x equal to sine square theta. Okay, so and if we differentiate both sides, then we will get dx equal to 2 sine theta into cos theta d theta. And now if we substitute this limit in this value of x in this equation, then we get beta m comma n equal to, this is our equation 1. If we substitute this value in equation 1, then we get beta m comma n. And also the limits will change. If we put value of x 0, then we get here pi by 2. If we put here x equal to 0, then here we get 1. If we put here, then here also we will get 0, because sine 0 is 0. So our lower limit will be 0, and if we put 1 here, x equal to 1, then we will get here pi by 2, because sine pi by 2 is equal to 1. Okay, so here pi by 2, because sine pi by 2 is 1. Sine pi by 2 equal to 1. So now we will, here in place of x you have to put sine square theta. So sine square theta raised to m minus 1. Here 1 minus sine square theta. 1 minus sine square theta raised to n minus 1. And in place of dx you have to write 2 sine theta into cos theta d theta. Okay, so it will result into 0 to pi by 2 sine square theta m minus 1. 1 minus sine square theta is equal to cos square theta. So cos square theta n minus 1. This 2 we will write here outside, and this sine theta into cos theta will remain as it is. Okay, so now we can rewrite this equation as 0 to pi by 2. Rewrite this equation, then we get sine, this is 2, so sine theta, this 2 will get multiplied with m minus 1, so we get 2m minus 2. Again cos theta will also get multiplied with n minus 1, so here we will get 2n minus 2. And the sine theta and cos theta will remain as it is. Okay, so we get 0 to pi by 2. Now this sine theta and sine theta, if we multiply them, then we get sine theta 2m minus 2 and plus 1. They both will get added as they are in multiplication, so we can write sine theta raised to 2m minus 1, because 2m minus 2 and plus 1, that is 2m minus 1. So here also cos theta 2n minus 1 d theta. Okay, and hence we got the property number 2. So we proved that beta m comma n is equal to this value, and hence we proved this property. So hence proved. Okay, so this is the property 2 of beta function. So now we will see property number 3. So this is the property 3 of the beta function, that is beta m comma n is equal to 0 to infinity x raised to m minus 1 upon 1 plus x raised to m plus n dx. Okay, Here also we will use the standard definition of beta function, and by using this property 1 we will prove this for property 3. Okay, so we will write property number 1 here. According to property 1 we can write that beta m comma n is equal to 0 to 1 x raised to m minus 1 1 minus x raised to n minus 1 dx, where n and m are greater than 0. Okay, so for proving the property number 3 we will put x equal to 1 plus y, x equal to 1 upon 1 plus y. Okay, so for proving this property number 3 we will consider value of x as 1 plus y, and differentiating both sides we get dx equal to minus 1 upon 1 plus y whole square dy. Okay, now from this equation we can also get value of y, that is 1 plus y equal to, if we take 1 plus y equal to 1 by x, then we can write y equal to 1 by x minus 1. Okay, so this is the value of y. Now whenever we will put x equal to 0, we will get y equal to infinity in this equation, and whenever we will put x equal to 1 we will get y equal to 0. Okay, so now if we substitute this value in the equation 1, then we get beta m comma n equal to 0 to infinity 1 upon 1 plus y raised to m minus 1. Here 1 minus value of x you have to substitute, so 1 minus 1 minute, light issue. So here also you can write, in place of x you can write 1 upon 1 plus y whole raised to n minus 1, and in place of dx you can write minus, this is our dx, so minus 1 upon 1 plus y whole square dy. Okay, so now solving this equation we get, in place of x equal to 0 you have to write, here it will be infinity and here it will be 0. So infinity to 0, 1 upon 1 plus y raised to m minus 1, and here if we take the LCM then we get 1 plus y minus 1 upon 1 plus y whole raised to n minus 1, and this will remain as it is. Okay, so this one and this one will get cancelled, so we can rewrite this equation as 0 to infinity 1 upon 1 plus y raised to m minus 1, and here that 1 and 1 got cancelled, so we get y upon 1 plus y whole raised to n minus 1, and here minus 1 upon 1 plus y whole square dy. Okay, so now solving it further we can write infinity to 0. If we take this y raised to n minus 1 here, then we can write y raised to n minus 1 upon 1 plus y. So we are multiplying both the equations, that is this both equations. So this will come here, y raised to n minus 1, and here we will get 1 plus y raised to m minus 1 plus, this is our n minus 1. Okay, and this term will remain as it is. So minus 1 and this minus 1 And so we can, this minus 1 and this minus 1 is equal to minus 2. So we can write y 1 plus y raised to m plus n minus 2, minus 1 minus 1. Okay, and here this term will remain as it is. And now if we multiply this both, then we get infinity raised to 0, infinity to 0, y raised to n minus 1. This minus sign will remain here. So we get 1 plus y m plus n minus 2, and this term will be also multiplied, so plus 2 dy. Now this minus 2 and this minus 2 and this plus 2 will get cancelled. Okay, so we can write 0 infinity to 0 minus y n minus 1 upon 1 plus y raised to m plus n dy. But as I told you that there is one formula that if you want to change this limit, then you can, if you want to remove this negative sign, then you have to change the limit. So as we want to prove the property 3, as we want to prove the property 3, we have to change the limit to 0 to infinity. So and we have to remove negative sign. For removing negative sign, so we will write 0 to infinity y raised to n minus 1 upon 1 plus y raised to m plus n. But we all know that we have to prove this, and we got it in the term of y. But we all know that beta m comma n is equal to beta n comma m according to property 1. So here in place of y you can substitute x. So we can write 0 to infinity x raised to m minus 1 upon 1 plus x raised to m plus n. Okay, so hence we can prove this property 3 of beta function. So hence proved. Okay, so these are the 3 properties of beta function. Thank you everyone. I hope you all liked my video lecture. Thank you.